So Gagan here, and today we have an exciting topic to explore. We're going to dive into the world of text generation, and we'll be using a powerful tool called the LSTM or long short-term memory network. You might be wondering, why did we choose an LSTM over a standard recurrent neural network for this task? Well, the answer lies in LSTM's ability to capture long-range dependencies in the data, making it particularly well suited for tasks like text generation. Now, unlike traditional RNNs, LSTMs can remember information over longer sequences, which helps in generating more coherent and contextual relevant text. Now, before we get started, one of the primary steps in text generation is to obtain a substantial and relevant corpus of text. Now, in our case, we'll be using the classic Pride and Prejudice written by Jane Austen, which is freely available from Project Gutenberg. Now, Project Gutenberg, it's a treasure trove for all those who are seeking a rich data set to hone their text generation models. Now, once you visit this website and click on any relevant book that you want to use for your text generation process, we can download it in various formats. So you can read it on web, and you have an HTML format, but we'll be using the plain text UTF-8 format. So once we have our text, the next hurdle is framing the problem for our LSTM model, and we'll be transforming the text into sequences of characters, each of a specific length, and our model will be trained to predict the next character in that sequence. Now, it's like teaching the model to anticipate the upcoming character based on the preceding ones. Now, let's quickly switch to our Visual Studio and look at the code that we have written for this. Let's take a closer peek at our Jupyter notebook code where the magic unfolds. Let's before we do that, let's quickly glance at our text itself. So this entire novel of Pride and Prejudice has been downloaded, and as you can see, I made sure to remove all the preface that starts for any novel. So we just directly begin from the chapter 1, sentence 1, and this is how the text looks like. So we load them into the I load the text into the file, and we open them using the encoding. And then what we're doing here is basically converting it into lowercase, and then the text is mapped to integers using a dictionary for efficient processing. So this code does the character to integer mapping, and we're just looking at the number of characters that we have and also the unique vocabulary. So we have 728,463 characters and 67 uh, unique literals in our text corpus. So let's look at how we can start defining our sequence. That is, basically we convert this text into a labeled data. How do we do that? We take the first 100 characters, and we want our model to predict the 101st character. So we define the x to be of sequence length 100 and y to be the corresponding 101st character for this particular sequence. So we use this for loop where we append each sequence and its corresponding character to integer of the 101st character. Then we look at how many sequences we have. So we have around 728,363 number of patterns. And let's start defining our LSTM. So before we do that, LSTM expects the input tensors should be in a particular way. So the dimensions of the input tensor should be batch size followed by sequence length and the number of input features. So our batch size would be the number of patterns that we have. The sequence length would be 100, and we want one character as input feature. So every time that is going to the LSTM cell. So this code here, and this code is for normalizing it. So it is a good idea to normalize our input tensor floating values before we send it to an LSTM model or any neural network perhaps. So we convert the target variable into a tensor. Then we look at the shape. As we discussed, we have these many sequences of each 100 and one input feature from that, and these are the number of y or target features or target variables that target values that we have. Now let's quickly look at the very first model that we're going to use. So we're going to start with a single layer LSTM model which takes one input here. So this CAR model we inherit from the nn.model class, and we define our LSTM layer here, input size of 1. So one feature goes in at each time step, and at every time step the hidden state or the hidden size vector we define it to be of 256 length, and we have one layer for this first character model. Then we define a dropout layer to prevent overfitting. So we define the dropout ratio to be 20%. That means only 20% of the neurons will be active during the training process. And we defined a linear layer here. This fully connected layer, we output the number of vocabs, since we have 67 unique characters, which will be our output. And one last important point to note is that at every intermediate time step, we'll be producing intermediate results. And since this is a sequence to one LSTM, we're only interested in the very last character that the LSTM provides. So we just take the very last output as our prediction, and we give it to the dropout layer here. So I just visually drew what I just explained there. This is the hidden state. Since it's an LSTM, it will also have a cell state, then 20% dropout layer, then we have a linear layer followed by the output. Now let's quickly look at the very important training function. So this particular block of code is for training the model. So we defined 148 to be the number of epochs, batch size to be 128, and we are using Adam optimizer and then cross entropy loss. And we use this very useful and handy function called data loader that's going to load the data for each iteration in terms of batches that we define. So for each epoch, so one key aspect to note here is we defined a best model variable in order to save the model that performs really well during the training phase, that has the lowest loss will be saved to this model. We defined a best loss. So this is standard training code. and we set it to the evaluation mode. After it does the back propagation, we compute the loss again, and we compare each iteration's loss to its previous loss. And if it's less, we are just storing that particular model weights and biases into this best model. So for at the end of all this training, we are going to export the state of that best model which has the lowest loss into this single cat.pth. So this took around 10 hours to run. So there's a slight error here because I defined the dict to be cat or dict, but I just changed it to cat or int. So this didn't hamper the training process anyway, and we just saved the best model here. So the next part would be to use this best model to generate. So for that, we need to load this best model. So this code here, we are using it to generate the text. So we defined a sequence of length 100. We just randomly take a sequence of length 100 from our text and then use it as a prompt and let it generate. So as you can see, we load the best model we have and then use that best model. So we create another class here because in order to load the best model, it requires another model object. We load it using this function load state dict, and then we pick one random sequence of 100, which is in pattern. So once we have our pattern, as you can see, this yeah. So this model is going to produce one character at a time. So we need to loop over in order to produce sentences. So this code here, it reshapes the X. Then we go to result. Then we print the result here, and there we go. This is output. So as you can see, this is the prompt, and this particular section is the output of let's say what's the length. So 1000. So this is of 1000 length. As you can see, most of it is quite irrelevant. It doesn't make any sense. It says case here, the case. It does fine here, the war, but most of it is not that good. There's mention. It gets mentioned, and it's probably this is probably soon. And yeah, as you can see, it does not do a decent job, but this still is a very good starting point. This is just one layer LSTM. Now let's look at another LSTM with two layers so that it can identify more complex patterns. So what I did is I just ran the same code again, but this time I made sure to use another layer in the model. So as you can see, number of layers here is 2. So this is a bit complex, and this is going to take almost double the time, but it ended up taking what? So this ended up taking 31 hours for the 40 epochs. So as you can see, I saved it into another file called single cat2. So I took another notebook here. I just loaded that best model here. And as you can see, this time when you look at the prompt, it looks more promising. So this is the prompt. It says, I have been to blame. I'm not afraid of being overpowered by the impression. It will pass away soon. So I think this still here is our prompt, and this is our response. It says, enough. Do you suppose them to be in London? Yes, where this is probably else. Can they be so well? This is probably concealed. And this is probably Lydia, used to want to go to London. Added Kitty, she's happy, then said her father. So as you can see, this does brilliant job. So just adding another layer can make a significant difference in the output. So the model can capture more complex relationships and and can produce more coherent and contextually appropriate sentences. So that's all for this tutorial. Thank you and have a good day.